Good afternoon, everyone. Yes, my name is Yoshi Kaneda, Kagawa University, from Japan. And my colleague, Benoit. Benoit-san, please.
Yes, Benoit Dory with CTBTO.
This session is T3.1. Yes, seismic and hydroacoustic and infrasound technology and applications. It's very broad as a field. So already on Tuesday, the e-posters already presented, it's completed. All posters is very, very important and interesting and significant. And today, I would like to invite 3 speakers on the oral presentation. I would like to introduce the first speaker. The title is just a moment.
Yes, so for the first speaker, who will present us one of the well-known techniques used during the geometry of design of the geometry of a seismic array, is the array response function. So please welcome Dr. Peyrov, who proposes an automatic optimization method based on a fuzzy self-tuning particle swarm optimization.
Please.
Hello, everybody. I'm going to share with you the result of my study on the seismic array design based on the array response function optimization method. I would like to begin my speech by showing you this excellent figure made by Dr. Gibbons, which compares different IMS seismic arrays in terms of their size, number of stations, and their configuration. As you can see, IMS seismic array size varies from small to large aperture. They usually have 10 to 20 sensors, and they are mostly configured in a circular shape. We can see that all the arrays are designed in a routine standard procedure. But what if we encounter some constraints during the practical array design? For example, if we need to design the array with a fewer number of stations, or we have some difficulties in the site selection, or generally we encounter some conditions that forces us to design the array in a flexible shape. Well, this speech is going to address a solution to this kind of problem. We have considered the array design as an optimization problem, and in this flowchart, I've tried to show you the main steps of our approach. It consists of 6 main steps. First, we construct the model space by setting the initial parameters, including array aperture, interstation distance, and the location of the reference station. Next, we build the initial model by setting the number of array station and calculation domain. In the third step, we will find the best array geometry using an optimization method. The next 3 steps, we will try to validate the optimized array in terms of its relocation power. Basically, we will use the synthetic waveform modeling to validate the location of the synthetic earthquakes and measure its accuracy. So, to find the best array geometry, we have applied fuzzy self-tuning particle swarm optimization method. It's a variant of the original PSO, which is a global optimization method inspired by nature's social behavior and dynamic movements of a school of fish or a flock of birds. PSO tries to optimize the global best solution by moving the particles within a swarm inside a very bounded search space. For doing that, PSO needs to, we have to set some parameters such as social factor, cognitive factor, inertial weight, minimum and maximum velocity of the particles at each iteration. Unfortunately, PSO setting is case dependent, and finding the best values for these parameters requires intensive research. But hopefully, FST PSO benefits from the fuzzy logic to adaptively select these hyperparameters. And also, it's fast and user-friendly. As you can see here, I have implemented this method in my code only by defining the search space and the fitness function. So it's really easy to implement. So let's see how we applied our approach in practice. First, we need to construct the model space. For doing that, we have constructed a grid of candidate stations around a predefined reference station. Next, 7 stations are randomly selected to construct the initial model. The ARF optimization will work around this starting model. But what is ARF? Array response function is an estimation of array resolution to identify a specific seismic phase. Actually, it's a 2D filter that operates on the incoming wavefront and shows the array gain in terms of a power density for the selected part of the signal. And mathematically, we can calculate the ARF by this formula. It mainly depends on the frequency content of the incoming waves and the relative position of the sensors. So let's see the ARF or initial model. As you may notice, our randomly generated array shows a bad ARF. It's very spiky, and it's too far to represent the ARF of the ideal array, which should be which should shows the Dirac pulse. So we have to modify the position of the sensors to achieve a better model. For doing that, we have defined an objective function, which is the average value of the beam power across the slowness domain. In a simple words, it tries to maximize the main loop energy while minimizing the side loop energy. This is the optimized array, its geometry and its ARF. We can see that the ARF is improved a lot. The maximum energy of the main loop is increased highly, while the energy of the side loops are decreased a lot. And we can see that our optimization, during the optimization, the fitness function is improved. So it seems that the optimization is working fine, but we want to validate it further. For doing that, we have applied synthetic waveform simulation by setting the input parameters of the synthetic earthquakes and the velocity model. And we had put the synthetic earthquakes at 450 kilometers away from the location of the suggested array. And we have applied the beamforming on the synthetic records at the optimized array. As you can see, the the main energy points the slowness 0.15 second per kilometer, corresponding to the regional P phase. And its back azimuth fairly points the correct position of the synthetic earthquakes. But also we can see a small error in the back azimuth, which is related to the azimuthal direction discretization, and mainly depends on the azimuthal beam size. So for further validation, I have applied another test, which I have relocated the synthetic event using our regional seismic network. You can see the locations in this figure alongside with the relocation parameters here. I want to focus on the absolute epicentral error, which is approximately calculated at 15 kilometers for the both methods, which kind of confirms our array is working and locating the synthetic earthquakes with a reasonable accuracy. In conclusion, this study shows that ARF optimization method is an efficient approach for designing arrays with flexible shapes. And also FSTPSO is a fast and reliable optimization algorithm for this task. The optimized array locates the regional synthetic earthquakes with reasonable accuracy, and its accuracy is also comparable to the regional seismic network. Thanks for your attention.
Very nice presentation. Any questions or comments? No? Okay, so I have some questions or comments. So usually the ARF, you're using the fuzzy self-tuning method. But I'm a seismologist. Usually I use the green function to the resolution function as a transfer function. Which is better? Why do you apply to the fuzzy self-tuning method?
The self-tuning, the FSTPSO is just the method for our first step to just optimize the geometry of the array. But for the second part of our study, we have implemented the modeling, synthetic modeling, which requires to generate a Green's function and then apply the force and then record the waveforms at the stations. But I just, due to the limited time of this presentation, I just skipped that part.
Okay, thank you. Yeah. Thank you very much. Any questions or comments, please?
Just a small question. On the IMS network, we sometimes have the challenge that we have to relocate an element. Yeah. And one of the constraints that we have to take into account is also some specific, I don't know if you have a river or some geography that constrains also the geometry. Can you take into account these constraints, or do you plan to?
Yeah, I'm really glad that you mentioned this part of the array design. Actually, the goal is what you mentioned. We can exclude some specific regions inside our search boundary, and then the optimization will work around all the space except those excluded regions. So we can exclude rivers, steep slope topographies, everywhere that we don't like to deploy a sensor. So that's the main goal of this work.
Thank you. Excellent.
Thank you very much. Yes, I would like to move on to the next presentation. So the title is the Interlaboratory Comparison on Infrasound Sensors. The speakers, Dominique Rodrigues. Please. It's okay? Please.
Okay, so thank you very much for the introduction. So I'm Dominique Rodrigues from the RNI, the National Meteorology Institute in France. And so I have the pleasure to present here in name of the laboratories mentioned here the results of an interlaboratory comparison on infrasound sensors organized recently. So I don't learn nothing to you here by saying that the CTBTO has the responsibility to promote and be ready to upload the nuclear test ban 20. And one of the main instruments used for the verification regime is the EMS. So the PTS underlines the importance of ensuring the data quality. This is true in the operational manual, which provides some specifications, but also in the quality assurance program for infrasound measurement system presented at the working group B more recently. So this, of course, includes the need of use of accurate and regularly calibrated measurement systems. So the traceability, as introduced in the quality assurance infrastructure, involves many actors, from the primary calibration, which is usually the responsibility of an NMI, passing by the secondary calibration, involving service providers like expert labs, accredited labs, or even manufacturers, and up to the on-site, calibrations involving PTS or other service providers. We have to be sure that when we ask a service of calibration to one of these service providers, they will deliver the same measurement, the same quantity within their claim measurement uncertainties. And so this is the main objective of the interlaboratory comparison, is to check the ability of laboratories to deliver accurate and equivalent calibration results. So concretely, what we do, we will test the same sensor by different laboratories, and we will compare the results. The benefits for the participating laboratories are a lot, like the validation and verification of the calibration methods, the identification of any problem, or up to, etc., to the validation of the claim uncertainties. There is many benefits. It is also maybe one of the main requirements for accredited laboratories in the standard 17025. So this is a very important point. So a point of history in infrasound comparison. So it is not the first comparison organized in this field. In 2015 and 2016, 2 pilot studies were organized. So maybe some of you remember that the result of these 2 pilot studies were presented at the ITW in Tromsø. And so from these 2 pilot studies, they reached to some conclusions and recommendations, like to include monitoring of the sensor stability, to use to evaluate rigorously the uncertainties of measurements, to use also reference sensors traceable to the SI. This was a very strong recommendation. Use as far as possible standard procedures to determine the influence of environment, and of course to use a technical protocol accepted by all the participants. So after that, it was agreed to prepare a new comparison by taking into account these recommendations, and so this comparison has been denoted PTS-AVH AC1 as the first formal interlaboratory comparison organized by CTBTO. So here's the technical protocol. So comparison was organized by CTBTO. LNE was a pilot laboratory of this comparison, and it involved 6 laboratories, CEA from France, LNE from France also, PSU from USA, PTS from Austria as an observer, Sandia from USA, and finally UMIS, University of Mississippi from USA also. So 6 sensors were circulated, 2 microbarometers, MB 2005, 2 microphones, BNK type 4193, and 2 static pressure sensors, CETRA type 278. So the sensors were circulated in turn between around approximately 6 months, between June 2020 and January 2021, and the stability of the sensors were monitored, of course. So here, some description of the participants' measurement system. So the CEA used a comparison method by using an active coupler, So the reference sensor here was a microphone at BNK tip 4160. LNE used two different methods. First, for the calibration of the microphones and the CETRA barometers, LNE used a primary calibration method, the laser piston phone method. And for the calibration of the microbarometers, LNE used a comparison method, the same device, but as an active coupler. And by using a reference microphone BNK tip 4160. PSU used the facilities from Sandia for their calibrations by using a primary calibration. It's a very original implementation of the reciprocity calibration technique on a very big cavity. Sandia used a comparison method by using two reference sensors. For high frequencies, a microphone BNK tip 4193, and for low frequencies, a CETRA tip 278. Like UMIS used also a comparison method with a coupler very similar to the one of Sandia, and with the same reference sensor, a microphone 4193 for high frequencies, and a CETRA for the low frequencies. So, some about the method for the analysis of the results. So, to analyze the results, we will need some performance statistics. These performance statistics are both the reference values and the degrees of equivalence. Here, the reference values, in some way, are the values to which the laboratories have to target. So, they are determined here by using a standard method, a standardized method, by using a specific algorithm given in this standard. So the reference value in this graph and in the following graph is represented as a target, so the zero axis. The degrees of equivalence are specific to each laboratory, so it represents the deviation between the result provided by the laboratory and the reference value. And it is associated to these degrees of equivalence, one uncertainty, which include both the variance of all the results provided by the laboratories, but also the measurement uncertainties as claimed by the laboratory, which is also represented here in these figures by the shaded area. So, for people not familiar with the interpretation of degrees of equivalence, how to interpret them, we have three different configurations for this case here. When the degree of equivalence and the uncertainties do not cover, the reference value, so this is a clear situation of failure performance. At the contrary, when the degrees of equivalence and uncertainties cover the reference value, it's a clear situation of successful performance. And with this method of analysis, we have a situation also of warning when the degree of equivalence and uncertainty cover the reference value, but not the measurement uncertainty, or the measurement uncertainty seems to be too small. In some way, it seems to be too small given the variance of the result provided by all the laboratories. So this is a situation of warning, and here the laboratories are only encouraged to address and to confirm the validity of their measurement uncertainties. Okay, so here's the results for the microbarometers. I will present only the results for the microbarometers because I don't have time enough. And anyway, they are representative of all the results obtained in this comparison. So on the left, the raw data obtained for the two microbarometers as presented by all the laboratories. And on the right, the degrees of equivalence for the 5 laboratories participating to this measurement. As function of the frequency. So as you can see here, we have situations of successful performance for all the laboratories, all frequencies. Expected maybe some situations of warning regarding the claimed measurement uncertainties for lab 4 at the lower frequencies, and maybe also for lab 2, maybe at lower frequencies. So this is an interesting result. Here for the phase of the frequency response, so as the same on the left, the raw data, on the right, the degrees of equivalence. So here we have one situation of failure performance for lab 2 at 1 Hertz, for the point 1 Hertz. For the other points, we have situations of successful performance. The degrees of equivalence are okay. Maybe also some situations of warning regarding the claim measurement uncertainties for lab 4 at low frequencies, and also for lab 1 at frequencies around 0.1 Hertz. So here, these laboratories are encouraged to review the uncertainties, to check them. Okay. Last result for the sensitivity. So the sensitivity is an absolute sensitivity, while the frequency response is a relative one, just to precise. So at 1 Hertz, sorry, sensitivity is at 1 Hertz. So you have here the degrees of equivalence in amplitude and in phase for all the laboratories. We have a situation of failure performance for lab 2 for the phase, and a warning regarding the claim measurement uncertainty for lab 4 for the phase, also for the other points. All is okay, we have situations of successful performance. Okay, to conclude, so the main objective of this comparison was to establish the reliable equivalencies for calibration of infrasound sensors. So you can say that there is successful performance observed for almost results. It remains some at specific frequencies, and for some laboratories, a few cases of failure or warning, and the laboratories are now working to improve their system or their calculation of uncertainties to improve these few points. But I would like to insist here more in the strong progresses achieved since PS1 and PS2 in comparison to this new comparison. And you can see here the degrees of equivalence for the same 3 laboratories which participated to PS2 and C1 comparison for a calibration of a microbarometer. So as you can see clearly here, in C1, the uncertainties decreased significantly, fitting now very well with the 5% tolerance limit provided in the operational manual. So this is a very important progress and interesting. We can see also that some issues observed at low frequencies in PS2, we can observe deviations around 2-3 dB, which is significant. These issues were solved also now in C1. So these results provide big confidence in the results provided now by the laboratories. Okay. So in terms of impact, this impact in the metrological traceability chain, this comparison involved an NMI and expert lab. So the results provided by this comparison support directly the data provided by this institute. So the 2 first steps of the metrological traceability chain, but by definition, the metrological traceability chain is an unbroken chain of calibration. So it provides also confidence in the data produced at the lower stage of the traceability chain, so up to the on-site calibrations steps which are under implementation by the CTBTO. So thank you very much.
Thank you very much. Nice presentation. It's a very important presentation. Any questions or comments? Comments? Questions? Please. Just a moment. Microphone. Please.
Question from the structure of the comparison and the reference value. The LNE was taking part on par with the other laboratories. So they all contributed in the same way to the reference value, or did you provide the reference value as an MI?
No. LNE has the same role of the other laboratories. So in this standard, the method, I will not detail here the method because there is a specific algorithm for that, but it's like an average. It's not an average, but it's, yeah. But the LNE has the same role that the other laboratories in this comparison.
Okay, thank you. Any questions, comments? You have?
Perhaps,
Please.
Dominique, if you can comment on how often you think such exercise should be repeated?
Usually at the BIPM level, we make comparisons it's normally in the accredited cycle, it's each 5 years. It's not easy to have a comparison each 5 years. This is the target, I think, but it could be more. But 5 years, it's a cycle of accreditation, so it's a good way.
Thank you.
Thank you. I would like to move on the next presentation. Thank you very much. Thank you very much. Yes.
Thank you, Dominique.
Next presentation is the title is a little bit long. Determination of the frequency response of the seismic and infrasonic international monitoring system station sensors using the on-site calibration approach. The speaker is Michaela Schwardt. Oh, please. Oh, thank you. Sorry. Her name? Okay. Dr. Schwartz. Yeah. Dr. Schwartz. Please.
Okay, good afternoon, everyone. Probably most of you have seen this morning already in the metrology workshop, so I hope it won't be too much repetition for you. Yeah, thank you for the introduction. I will focus mainly on the seismic sensors, but if we have time in the end, we can take a look at the infrasonic calibration as well. To start with, why do we have a need for on-site calibration procedures? And Dominique already pointed it out, that is a requirement from the CTBTO. And in the low frequency range down to 0.01 hertz, reliable calibration procedures, which include traceability to SI, are currently missing or, well, are currently being established. So we have to rely on the manufacturer's specifications. As you can see here, I plotted the amplitude and phase response for a GS13 from a just random database. And when we now take the GS13 to a lab where it is calibrated, we see a deviation from it. So the calibration in the lab is very important, and now we have to move that traceability from the lab to the stations on site. And this is one of the main goals of the Infra AUV project, of which most of you have probably heard by now. They do not only develop primary and secondary calibration methods, but also on-site calibration methods. But here we have to focus, especially in the IMS context, that the developed methods do not interrupt the ongoing operations of the system. And another point that we have to consider, besides traceability, is the uncertainty as well. So if you're interested, check out our homepage from the project. And well, as I said, the laboratory procedures are quite well developed by now, thanks to the project, but the field sensors aren't able to come to the laboratory on a regular basis, as this would disrupt the measurements and violate the technical requirements, especially of the IMS. So somehow the field sensor, the laboratory has come to the field sensors. And this is very important because in that way, if all stations are traceably calibrated, they can be compared. Okay, so somehow we have to install a reference from the laboratory at our field station and use a suitable method for it. So luckily, from the infrasound perspective, there are already methods developed, and we try to use them for the seismic sensors as well. So we already have a lot of calibration methods for seismic sensors, but most of them are just relative and not traceable to SI. So we took the approach from the infrasound, so the Gabrielsen method, what we call it, and applied it to our seismic sensors. So we have a traceable calibrated reference from the lab and bring it to our station sensor, which is called SUT at the moment. We have some requirements. So both of the sensors have to measure the same coherent signal, and to ensure traceability to SI, our reference has to have a known response. Just a quick view at the algorithm. So we start with a raw data signal, either a seismic signal or infrasonic signal, just like a whole day. We filter it within different passbands. And then from this filtered signal, we take a segment. The segment length depends on the frequency range we're looking at. And again, we take segment I in this case, and take some overlapping windows. And within these windows, we calculate similarity measures cross spectral densities and outer spectral densities, which we need in the method to calculate a gain ratio between those two sensors. And with this gain ratio and the response from the labs, we are able to determine the frequency response of the sensors. So that's the theory. Now we take a look at our field test. So we had in total three calibrated sensors we took to our station in the Bavarian forest in Germany. And we co-located the sensors to our station sensors. The whole experiment lasted for about 260 days. And now one of the sensors is back in the laboratory for recalibration because we had some slight issues, I would call it. But the other two sensors are still at the station. So more of data coming in. I like to start with the comparison of our three component seismometers. So they are spaced very closely at the moment, in our vaults. So the station sensor is a CMG sensor, and which is also the sensor on the test, and our reference is the STS2.5. As I said, we had 260 days, and I took two different similarity measures for my calculations. And after all 260 days, I was able to calculate a mean gain ratio, in this case for the amplitude, and from that we can see that we have low standard deviations in the mid-frequency band and high standard deviations on both sides, which we have still to take a closer look at. And from that we could estimate an amplitude response. But we not only used the vertical component as said here, but we also looked at both horizontal components and at the phase as well. If you see these plots for the amplitude on the left and the phase on the right, in comparison with the theoretical values provided by the manufacturer or by databases, it actually looks quite fitting, but we have some deviations on this side. So I faded them out here because the measurements from the laboratory are currently not fully reliable, so we have to take a closer look at that as soon as the sensors are recalibrated. But as a first field trial, the results look quite promising. As I mentioned before, we have different seismometers at our station, and we wanted to have like a short cross-check. So is the method working? So we compared two calibrated sensors, in this case the GS13 and the STS2.5. Caution had to be taken because they have different preamplifiers and digitizers and so on, but this is not of interest here. But in total, we were able to, again, derive the response function for the GS13 in that case. If we look at the comparison between the theoretical values and the obtained values, I was first a little bit, disappointed. But then I looked at the values provided by the laboratory, and the method actually works quite well in that case. but we observed the similar behavior for the higher frequencies, so we still have to take some cautions for the higher frequencies. The next question is, how many references do I need for my whole seismic array? So the first speaker already showed a very nice plot of the different arrays we have in the IMS. So is one reference enough? Do I need one reference for each seismometer? So I took a quick look at it. We have 2 calibrated references, 1,400 meters apart at our station. And I calculated, again, the gain ratio, for the sensor and the test, and the reference, which are both G13, and the response function from it. And because both of them are calibrated, I could switch the sensor under test and the reference, and we basically see a similar behavior and a similar result for it. I have to mention here we had a lot of coherent signal below 1 Hertz and not a lot of coherent signals above 1 Hertz, so we might have to wait a little bit longer until we have trustworthy results. So to sum it all up, we have an added value through the on-site traceable calibration, especially if we compare that to the so-called electrical calibration, which is shown here in green, because the on-site calibration values are much more closer to the laboratory values than the electrically obtained values, especially for the amplitude response. So what is the outcome of the project at the moment? Well, traceable on-site calibration for seismometers is possible, for infrasound station as well. And the biggest benefit is we don't have to interrupt any of our measurements. They can just keep running, and all technical requirements are fulfilled. However, there are still some open points like uncertainty propagation and the interesting behavior for higher frequencies. But we had some very nice discussions today, so this will be soon, hopefully, be solved, this problem. And if you are interested in more of the project work, visit our website. We have a newsletter, and stay tuned for more to come. Thank you.
Presentation. Thank you very much. Yes.